Professor Grigori Chapiro from the Universidade Federal de Juiz de Fora, also from the Department of Mathematics. Okay, thanks.
Thank you very much for the presentation. So I hope I will not take so long and we can lunch. This is a joint work with a lot of people. So Lucas Furtado from Columbia University, Dan Marchesin from IMPA, Fatih Özbak, he just finished his PhD under supervision of Professor Schechter in North Carolina State University, and my colleague Laura Senos from Juiz de Fora. And so the main objective here is that a lot of people, as we have seen already in this conference, and more are studying combustion waves, and always it appears some traveling wave solutions. But however, the rigorous existence and uniqueness demonstrations are not so easy to make. So there is an effort to put some mathematics, more rigorous mathematics in it. Well, I will speak basically about this. So I will give a little introduction where these combustion waves appear. Then I will present the model we are working on. I will state some previous results. Then I will show our current advanced. And if I have some time at the end, I will talk about stability. So basically, Jesus already told a lot about it. One of the ways, for example, combustion in porous media appears during in situ combustion. So the first idea comes from this paper, and the idea is you inject air into reservoir, you produce some combustion, it generates heat, heat spreads into the porous medium, generating a lot of things. For example, light hydrocarbon starts to evaporating, water became steam. Then there is a very difficult to understand cracking zone. There are more than 9,000 known reactions here, and well, people from chemists say that there are much more to be discovered. Well, then we have a coke zone. It's okay. I will talk about it later. So where there no reaction already happening, and then the oxygen reaches this coke zone and produce combustion. So this scheme, of course, it's not the most general one. This is high temperature oxidation scheme. There are others, for example, low temperature oxidation, and others, for example, Professor Bruining, Dan Marchesin, and Alexei simulated and studied this type of regimes. But I will talk about this. So, of course, to do rigorous mathematics, we need very, very simple model. So we are going to study one-dimensional, so a thin cylindrical reservoir filled with something like carbon, and we are injecting air. So, and there are two possibilities here. One is the combustion wave is going with the flow. So we have this gas flux here, and the combustion is going co-flow, and we have counterflow. So the combustion starts actually when here there is a carbon, so we fill it with air, and the combustion goes in the counterflow direction. Well, first, we usually study Riemann problems. I will not talk a lot about it because we have already 5 talks about what is Riemann problem, and Professor Dan, I think, will talk about Riemann problem at the last talk of this conference, at least by the name. And so it's basically PD with this initial data, and I will talk about traveling wave solutions, which are the following. So we have reaction diffusion convection system, and we will change the variables from xt to xi, where xi is a traveling variable, where v is a constant speed, and then we will look for stationary solutions. So this modification will generate this PD, and then we just take out this term. So we will look for stationary solutions for this new PD. If someone is really interested about it, there is a whole book of Wolpert and Sons about traveling wave solutions for parabolic systems, which have a lot of theory proved about traveling waves for this type of PDEs and systems of PDEs. Well, our group and close have a lot of works about the existence of this type of equations. So, well, we have these two papers about singular perturbation using Fenichel theorems. But it's, so I will not enter in details. However, so using singular perturbation, it's not so mathematically rigorous, because for nonlinear partial differential equations, there is no rigorous proof that guarantees existence. It's more like if there is existence, then the solution behaves in such way. And, well, we have some recent developments on mathematically rigorous solutions, proofs of existence and partially of uniqueness. So I will talk about this particular paper and what's going beyond. Well, for physical and mathematical formulation, we need a lot of hypotheses. So the flow will be considered one-dimensional. Immobile fuel doesn't vaporize and doesn't move. This is wrong. This is from another. I actually forget to take it out. So fuel occupies small part of the available space, so we don't consider changes in porosity during the combustion. Local thermal equilibrium means that we have only one temperature in the system, constant gas speed. I will not consider pressure and Darcy law. Heat losses are neglected to the exterior of my domain, and pressure variations are small. So the system we consider is this one. Here we have a heat balance equation, solid fuel mass balance, oxygen mass balance, and the Arrhenius law. So two principal things here are the simplification. We consider that both speeds are equal, so for thermal convection and for oxygen displacement, which is not true, of course. However, this is PhD thesis of Fatih Oxbak, now submitted as a paper. So it can be made by similar analysis for different speeds. Another very strong simplification is this one. So instead of considering a normal Arrhenius law, we consider it simplified. So it is possible to consider negative temperatures. And so phi for these temperatures is exactly 0. And the combustion rate obeys normal Arrhenius law only for positive temperatures. No, it's, well, we have dimensionalized it. So actually we have two-page discussion on how to make it physically less unrealistic in that paper of 2014. But so this is, it's negative from mathematical point of view, not from physical point of view. From physical point of view, it means that we consider 0 combustion rate until some point, and beyond this point, it obeys cut off Arrhenius. Well, so in the Riemann problem solution for this case, it appears two types of waves, contact waves, which can be standing, so speed 0, and some with speed A. So actually, as we have diffusion in our equation, so the temperature contact wave, it's not a really contact wave in the sense of conservation laws. It's becoming smoother with time. Just in order to simplify the presentation, I will call it contact wave. Well, before someone point a finger and say that I'm wrong. So I will call both of them contact waves with speed A, remembering that both of them have the same speed. And our notation will be that we exit some state, which I will talk in a second, come to another state, and the wave with speed c above it. So this notation means the wave that connects state fc to state tc with speed c. Well, what means this connection? So when I look for traveling wave solution, so if we go from our PDE system to ODE, we have this contact wave, which are really simple to understand. I will not even put them in my talk, and traveling wave solutions, which are really the complicated ones. So we have always this ODE system. The solution will always connect to equilibria. This is not so trivial. It's proved in this book of Vazov. And the equilibria, we will call them FC, TC, or OC, depending on which variable is 0. So FC means no fuel, TC means temperature 0 negative, OC means 0 oxygen. And then, so in the previous paper was proved that if the speed is positive, which means that we are injecting by the left side oxygen, so this is okay, and we consider only positive combustion wave speeds, then we proved this theorem. So there are only 4 types of connection possible. So from FC to TC, OC to TC, fast wave, and FC to OC, TC to OC, slow waves. This CF means that the combustion wave speed is faster than A. So if CF is bigger than A, I call it CF. If combustion wave speed is slower than A, I call it CS, slow. Well, and then we prove that, so there exists under some reasonable hypothesis, there is this connection, and for the fast wave as well. Well, if I put the solution of the Riemann problem, so of course we have a lot of cases, so this is a whole Riemann problem solutions for all possible left and right final states. There are 18 of them in this picture, and well, what it means. So if we start with cold reservoir and inject some oxygen, we can have, let's say, stationary fuel wave. Then we can go to some intermediate state which doesn't have the small temperature and no fuel. Then we have a contact wave, which lead us to another state of no fuel. And then we have fast combustion to again reach low temperature initial reservoir with no, so which can contain oxygen. So, and you can follow, you can, how to say, play with all these pointers and find all the 18 sequences. When I say 18, I mean always the maximum sequence. So, because of course, I have this one particular solution from OC to OC, but I always will consider the biggest sequence possible. Okay? Well, so this was done before, and our next step was generalizing this result by taking out the hypothesis that combustion speed is positive. So we take it out, and we could prove the following. So actually, there are 2 connections possible connections. We put a CC of counterflow, so it's negative speed. So the CC is always strictly negative. And we proved these 2 results. I would like to notice that here also they reach, we could prove that they reach the state exponentially. Well, and they exist, of course, under some very nice hypotheses. So the big picture of Riemann solution for, it's exactly like the previous one, only that we add more 3 pointers, and the maximum number of Riemann solutions jump to 26, if I'm not mistaken. So this is a nice picture. Then we don't need 26 lines to explain all of them. Well, I will give a little details on our results. So first of all, there are no combustion traveling waves of the system with negative velocity except these 2. The proof is really easy. It's basically thinking about that you cannot have combustion with no oxygen behind and in front and beyond the combustion wave. There is nothing to be burned. And the same for fuel. So, and this is actually the hard result, which says that there is a connection. There are 2 types of connections, and always this will be combustion speed. So the idea of the proof is the following. We take the parameter space, rho minus theta, rho minus c, so the speed. Always remember that for our case it's always negative. And we divide it in 3 regions. So C is a curve which corresponds to this formula. Below it, we have the region R1. Above it, the region R2. And we prove the theorem separately for all these three regions. It happens that from one of the regions, R1, the connection is always of one type, from another one is of second type, and on this curve C, we have, so what I'm talking about, we have three possibilities here, if you see. So we can do this counterflow combustion from TC to FC state, or from TC to OC state, or to the intersection. So what I'm claiming is that the intersection happens exactly on this curve C in the parameter space, TCOC above and TCFC below. So here I will only make a small resume of the proof for what happens over the curve C. And so basically what it happens is that we have the central manifold for the equilibria minus, so the left equilibria. And we have, so for the plus equilibria, right equilibria. And this is an unstable manifold of minus, so it's a left equilibria, where the wave is leaving. And we have this manifold, unstable manifold, stays above the central manifold. So what I'm trying to prove is that these both manifolds have an intersection. If they have an intersection, it means that there is at least one connection. Well, so we consider one limit case, this one, and we can prove that this happens, so this manifold stays above the other. And for the other limit case, where rho minus is infinity, we can prove that this manifold have a nice curve and goes back. So the unstable manifold of the left equilibrium stays below the central manifold of the right equilibrium, which make, so as the things have to be continuous, and so for some parameter in the middle, there is at least one value of rho minus, where the two, both of these manifolds cross, and then I have the connection.
Is the parameter A?
No, the parameter is rho minus. So there is at least one rho minus for which we have this nice connection. So this is, of course, there are 8 pages of proofs, so, but I can resume them in 2 pictures, so no one is sleepy until now. Now it's a little bit complicated because in order to prove the uniqueness, we only be able to prove the uniqueness over this curve C. We use Melnikov integral. So what it says is that Melnikov function, it measures how the split on the stable manifold occurs, and then if you integrate Melnikov function, so what's called Melnikov integral, and it doesn't change the sign along your parameter space, then you have only one connection. So it cannot generate another one. And, well, this is done. So this theory, the proof of this type of thing, so using Melnikov integral for this type of connection, was done by Stephen Schechter in '87. And actually, it can be applied even to more general cases when the equilibria are degenerated, which also happens in some problems of combustion. Maybe it's a good idea if someone wants, these calculations actually are really hard, so if someone wants to take it over, there is already a basic basis for proving uniqueness for solutions of much harder type. Well, next we can, of course, so this basically is a resume of our existence and uniqueness proof, and we want to show that it makes sense, so we make a simulation, numerical simulation, to show all these sequences. Here I will show only some of them. So if we start with some initial data and make a simulations, we can show that this sequence, for example, is possible. So this picture shows that this sequence is possible, and other ones as well. So for example, let's look at this one. So it shows that we start with this counterflow combustion, which goes from state TC. So you see the temperature here is negative. It goes to some state FC. So here the fuel is 0. Then we have a slow combustion from FC to OC. So here it is. We start with no fuel and end with no oxygen. Then we have a contact A wave from no oxygen to no oxygen. So this is this wave. We can see it here. And then we have another fast combustion from OC to TC. So no oxygen to small temperature. Well, yeah, I think it should be right to mention that these simulations were done with RCD code developed by Duilio Tadeo and Ismail, which I think is somewhere here. So, well, just 1 second about stability. Actually, these simulations, of course, show that the theory was makes sense, but also it shows that the waves are somehow stable, because unstable waves usually are not possible to obtain in numerical simulations. And someone can really study stability. There is a lot of papers in this sense, and this book have a lot of things about bifurcation points and stability. We also do it with Lucas Furtado. Well, and we have a lot of results, but I don't want to take a lot of time. Maybe just see some nice. Yeah. So we have some, even these simple systems allow some strange behavior, oscillating behavior for waves. So you see that not even, so simple system. Well, how I move? Oh. So even this type of simple system can present really strange solutions when you are not analyzing only the traveling wave, but whole the Riemann problem and how the waves interact with each other. Well, who is interested, I can, of course, pass the paper. So, I don't know. Thank you very much.